So today's class we will discuss about some of the additional problems with with respect to module 1, that is semiconductor diodes and applications. So here the problem is determine the germanium PN junction diode current for a forward bias of 0.2 volt at a room temperature 27 degrees with a reverse saturation current equal to 4.37. 4.37 microampere. So they have given. So here the temperature is given in terms of degrees Celsius, but while calculating it, while putting it into the formula, we have to convert in terms of Kelvin. So we just add it with 273. So it get converted to 300 Kelvin, where 27 degrees is room temperature. And voltage equivalent of temperature or thermal voltage, what we call the other way, thermal voltage or voltage equivalent of temperature, VT. It is given by T by 11,600. So this 11,600 is all final value after considering all the constant values, and the simplified value is 11,600. So T by 11,600 will be giving you, T is 300, it will give you 25.9 millivolt. So that is your threshold, the temperature voltage equivalent of temperature or thermal voltage. Now will the forward bias voltage of 0.2 volt. So V is given, and the saturation, reverse saturation current is given 4.37 microampere, and eta for germanium it is 1 and for silicon it will be 2. So this is the diode current equation which I had told you to remember. I is equal to Is e to the power of V by eta Vt minus 1. So this is the diode current equation. So if you are following any other textbooks, some textbooks have given derivations. So derivation is not there, only the diode current equation. You should remember that too. If they ask in problems, we might have to use this one. So now substitute everything, and you will be getting the diode current. So where Is is the reverse saturation current, V is the forward voltage, this one is our thermal voltage. So this is the constant with respect to the any kind of semiconductors material. So this gives you diode current. This is a simple for problem, but you should know to convert this voltage equivalent of temperature. So you have to get it by T by 11,600. This step you should know. Rest of the things is just substitution. After this, the next one is they'll give you a circuit like this. For the diode circuit shown below, find ID and V0, use approximate mode for the diode. So here, approximate mode for diode means the approximate mode is nothing but approximate model. So approximate model is nothing but our where diode is being replaced by a battery. The second model, whatever you have taken, no, that is the approximate model, or the second approximation model, whatever we have now. So according to that, we know that diode is going to act like a battery of 0.7 volt. So that's why we take this diode as diode voltage. So is 0.7, as we know that, because they are given it is SI. Don't expect always in the question they'll give you 0.7 or 0.3. They'll just mention in this, even you have to see in the circuit. If they just mention it as SI, that indicates that diode is silicon diode. So whenever it is silicon diode, you have to consider the PV, the cut-in voltage, drop-in voltage as 0.7. Okay. So now the circuit is given like this. So we are just going to replace this diode by a battery, because they're telling no, use approximate mode. Mode is nothing but approximate model. So approximate model will be using it. And now this is the circuit which is given. Similar kind of problem we have solved in module 1 already, but still will solve, not an issue. Here, so let us take the circuit 6 volt 1 kilo ohm. So 1 kilo ohm. So they'll be giving the circuit like this. They'll be not giving you the, sometimes they may not give you the closed loop circuit. So this circuit has to be rewritten as, so they are telling plus 6 volt. Plus 6 volt indicate that this terminal is positive. Okay. So this terminal is positive, no? So connect the positive terminal to this. So obviously the other terminal should be negative. So other terminal will be negative, which comes the lower side. This is 1 kilo ohm diode. As we are using approximate model, so we will be using a battery. So again, this is, you know, that this is anode part positive, this is cathode part negative. So this is positive, this is negative. So this is our ground. Usually the ground is the negative terminals only will be grounded, or we also call it as common points. Okay, the common points are the grounds or the negative terminals of the batteries will be usually grounded. After that, we are having the output. So the output voltage, even the output voltage will be taken across one terminal is positive and other terminal is negative. Okay. So why they might give you a load resistance? I don't think they are given load resistance in this case. So yeah, the load resistance is not given. So the load resistance is not given here. So but still we can find out the voltage, because you know that the voltage is always measured in open circuit. Voltage is measured in open circuit. Current is measured in short circuit. That's why to measure the current, ammeter is connected in series. To measure the voltage, the voltmeter is connected in parallel. Okay. Always we have to connect the voltmeter in parallel to measure the voltage. Ammeter in series. You should come here. You cannot connect the ammeter parallel like this. If you connect like that, no, the current will move through the ammeter only. The no current will flow through this, and you will be not able to find out what is the current which is flowing through this 1 kilo ohm. So that's why the ammeter always should be connected in series, and voltmeter should be connected in parallel, as you know that parallel branches will have same voltage. If you connect the voltage in the voltmeter in series with respect to any resistors or anything, then the voltage is going to divide among themselves. Because of that, we will be not getting what is the actual voltage across that particular resistance. So voltmeter should be always connected parallel, and voltage should be connected. Voltage will be always measured in parallel combination. So now we'll apply the Kirchhoff KVL, Kirchhoff voltage law. So this is one loop I'm considering, and after that this is the other loop I'm considering. Okay, so considering this loop, we'll write for the, this is, let us take this as loop 1 and this is loop 2. So what they have asked in the question, so find the forward equivalent circuit using the shown below given. So VT is the 0.7 volt, that is 0.7 volt. The question they are asking find ID and V naught. That means they are asking forward current, that is current which is flowing in the circuit, and also the output voltage. So first we'll apply for applying loop 1. So when you apply loop 1, starting from this minus to plus. So what is the voltage? 6 volts we are having. So this is 6 volt. And this one is 0.7 volt we are having. Minus to plus, plus 6. Coming to this, always I have told, consider the entering point as positive, leaving point as negative. So the current entering point to a resistor you consider it as positive and leaving point you consider it as negative. So plus to minus gives you minus, and when you apply KVL, as you know, you should write it in terms of voltage or in terms of current and resistor. You cannot write only current. Okay, current can be written only in when you apply KCL. When you apply KVL, you should not we should not consider only the current. Along with current, you should consider the resistance. So now let us take the current through this is ID. So we will take minus ID into R. R is 1 kilo, 1 into 10 to the power of 3. After that comes here plus to minus. So minus ID into 4 into 10 to the power of 3. After that plus to minus. It is minus 0.7. Again the loop got closed. That is equal to 0. So 6 minus 0.7, 5.3 minus ID into, in this 2 I can take uh, yeah I can take 1 plus 4, and I1 I can take 10 to the power of 3 common, that is equal to 0. So 5.3 is equal to ID into 5 into 10 to the power of 3. So this implies ID is equal to 5.3 divided by 5 into 10 to the power of 3. So you find out the corresponding value. So the corresponding value what we have got is 1.06 milliamps. That is 1.06. Since it is 10 to the power of minus 3, we can write it as 1.06 milliamperes. Now, after this, you have to find out the output voltage. So now apply KVL to loop 2. So when you apply KVL to loop 2, minus to plus, so the loop is in this way, the clockwise, minus to plus, plus 0.7. Coming here, when you consider this one, entering point is this one, plus, minus. Don't consider this one. We are considering this way, no? That's why plus to minus. Plus to minus is minus ID into 4 into 10 to the power of 3. Coming to this here, this point is positive, this point is negative. Plus to minus. Minus V naught is equal to 0. So already we know what is ID. So just substitute ID value. ID is 1.06, 1.06 into 10 to the power of minus 3 into 4 into 10 to the power of 3 minus V naught is equal to 0. This get cancelled, and we get 0.7 minus which we will get 4.24. So 4.24 minus V naught. So we will be getting on subtracting this one, 4.24.7, we will be getting 5, 3. So we'll be getting 3.54. So minus V naught is equal to 0. So V naught is equal to minus 3.54 volt. So this is how we are going to find out the output voltage. So if you want to apply the KVL in the opposite direction also, you can apply KVL. So there is no rule that you should apply clockwise only. If you want to apply it anti-clockwise like this, you can apply like this also. Okay. In any way here also you can apply anti-clockwise. Anyway, you can do. So this is about this problem. Now, after this, the next one is for the diode circuit shown below, determine V1, V2, V0, use approximate model of the diode. So here, while using the approximate model again, whenever they ask you to find out the approximate model, you have to consider this diode, silicon diode as 0.7. So silicon diode should be 0.7 and you'll be using battery instead of the diode. And but here the change what you should observe is they have instead of grounding this one they have given it as minus 4 volt. Okay, so it is not ground, it is minus 4 volt. That means here also you will be getting one more the battery you'll be getting. So this circuit, yeah. So how to write this circuit is, so there is a resistor, so resistor, diode, diode, resistor, that is minus 4. This is V in. It is connected like this. So if you are very confident, you can apply cable to this one and you can get it. But if you are not that much confident, then it is better to rewrite this circuit. So rewrite this circuit first. So this is plus, no? So consider a battery, positive, negative, and after that resistor, and this is as they are telling approximate model. See, if they are not telling approximate model, no need of considering silicon as a this diode, silicon diode as a battery. You can directly consider the voltage drop of that, and you can consider it as some V. Okay, now they are telling approximate model, so consider it as a battery. After that, resistor. So since they are showing it is minus, so make this as minus, this is positive, and after that, both these terminals will go to ground. And after that, take the output voltage. Okay. So now also you can apply the KVL to this, KVL to this, and you can find out the output. So this will be positive, this will be negative. Okay. So if it is negative given, if they have given the negative value, then negative sign comes upwards. If they have given positive, then our positive value will come upwards, negative value will come downwards. That you should remember. So this is how to write. After that, applying KVL that you can do. So just apply the KVL and you can do. So whether to write the entire circuit or not, it is left to you. But when they ask you to, it is an approximate model. They are asking it as approximate model. Then you have to replace this diode by a battery. At least that you have to show. After that, you can see here I have not considered the entire, or I have not written the entire circuit. I have just written the same thing, minus 4 volt. Okay, if you want If you are confident, you can do like this, or if you have any confusion, better write the circuit neatly and afterwards you apply the KVL. It is left to you. But in this question, what they asked is find out V1, V2, V0. That means V1, V2 means what is the voltage across this resistance and what is the voltage across this resistance, and after that what is the voltage at the output. To find out the sorry, not the resistance, but yeah, voltage across 3 kilo ohm resistance and what is the voltage across 2 kilo ohm resistance. So in order to find out the voltage across 3 kilo ohm, first we should know what is the current across this 3 kilo ohm, because we have the formula V is equal to I into R. If you know the current, then you can find out the voltage easily, because voltage is the potential difference between the two terminals. So when you know the current and resistance, you can easily find out the voltage by using the Ohm's law. So first we'll apply KVL to the inner circuit. The circuit we are applying the KVL to the input circuit. The circuit we are applying, and we find out I. When we find out I, since current is common to this entire loop, the current which is flowing through this loop will be same. So 8 minus 3 into 10 to the power of 3 into I minus 0.7 minus 2 into 10 to the power of 3 I plus 4, and you find out I. So when you know I, just V1. V1 is I into this resistance, 3 kilo ohm into I. So just you'll be getting 6.78. Similarly for V2, 2 into 10 to the power of 3 into I. Output, since say here you can apply KVL to this and you can find, or the output is taken between these two terminal, between this and this. Okay, so you can just consider the voltage drop across this resistance and this voltage. So what is the voltage drop across the resistance? The voltage drop across the resistance is 4.52. So what you can do is you can just consider 4.52 minus 4. That gives you 0.52 volt. Since here where when you consider the KVL here, since the output voltage becomes negative when while applying the KVL, it becomes negative, it will be minus sign. Okay, here we have just added it, but actually when you apply the KVL here, it will be negative. When you apply KVL here, so it will be negative only. So that's why the final answer is negative. This should also this should be positive and this should be negative, because on applying KVL here, uh, this becomes minus to plus. So this becomes plus 4 volt. But since we are applying the KVL in this way, so your output will be plus to minus, as we have seen in the last case. Coming to the next problem, for the network shown below, sketch V0 and determine DC voltage. So they are asking to sketch out the network and determine the DC voltage. So you have to write the circuit is been given, and here forward resistance is not given, and VT is also not given. So that means forward voltage is also not given. Then we'll consider this as an ideal diode. See in the exam, if they are asked, if they are yeah they have given no here the question itself they are told diode is ideal. That means the voltage drop is not 0.7 or 0.3. It is 0. Now, so we have to find out the output voltage. In order to find the output voltage and determine the DC voltage, they're asking. So in order to find the output voltage, we know that VDC is equal to Vm by pi. See this, how we got this Vm by pi is, see, whenever a circuit is having a single diode, whenever, see this is one circuit, it is having one diode. This is compared with a half wave rectifier. So when it is compared with a half wave rectifier, then the formulas which we have derived in half wave rectifier, the same formulas we'll be using here to find out the VM peak voltage and VDC, that is average DC voltage or DC voltage, whatever we are having. So we have already derived VDC is equal to VM by pi. So that's why we just convert, since they are telling it is in VRMS, 100 VRMS. That means it is in terms of VRMS. So convert that first to VM. So how do we convert that? We have the formula VRMS is equal to VM by root 2. By using that formula, we get VM is equal to 141.4 volt. We got VM. Once you get VM, it is easy to get VDC because VDC is equal to VM by pi. So don't think that it don't look like rectifier and all. See, they have given VRMS means that indicates this part is having AC signal. RMS always represent AC signal. Okay, so this VRMS indicates AC signal, and the single diode indicates the rectifier circuit. As you know that half wave rectifier is having single diode. So the equations which are applicable for half wave rectifier is applicable for a single diode also, because a single diode is going to allow half cycle to pass through this, and it will not allow remaining half cycle to pass through that. So that means it is working similar to a half wave rectifier, where even in the half wave rectifier also, during forward bias condition, the diode conducts. In reverse bias condition, diode will not conduct. Okay, so we got VDC. So this is the half wave rectifier. During positive cycle of VI, diode does not conduct. So diode will not conduct. So it is open circuited. So whenever it is open circuited, you can see that whatever the voltage you will get at the output side will be equal to input side, because you are measuring at these 2 points. So whatever the voltage you have, approximately the same voltage will be coming out here. Even though you have resistance here, so there will be not much drop. So it is almost ignorant. So almost output will be equal to input. During negative half cycle, VI, diode conducts, V naught is equal to 0. So when diode conducts and when you measure the output across this is what is this? This is a short circuit. Always you know that the resistance across the short circuit is 0. When resistance is 0, then automatically the voltage becomes 0. See, across this short circuit, there might be current. Current will flow definitely, because current always looks for a short circuit, because short circuit is a low resistance path. So low resistance path only the current will be obtained to flow. So here in this case, since it is short circuited, current will flow, but since there is no resistance, the voltage will be 0, because V is equal to I into R, and R is 0, automatically V becomes 0. So this is what the circuit. Suppose if they are telling plot the waveform, if they are asking plot the waveforms, then just plot the waveforms. This is Vi, this is our V naught versus time period. Positive half cycle, V naught is equal to V in, negative half cycle is 0. Or suppose if the diode connection is such a way that the positive half cycle will not conduct, means make this as 0, and negative half cycle will conduct, means show the negative half cycle. Don't worry about inverting, non-inverting, all those things. In rectifier, actual rectifier circuit, it gets inverted because of the presence of the transformer. Okay, but here, since we are not using any transformer, we'll write like this only. So only the second half is allowed to pass through. So it depends upon how what depends upon the direction of the diode. It depends upon the direction of the diode. So they don't expect them to give always the diode in this direction. They can simply they can give like this also. During that time when the current passes through like this, it becomes open circuited. When the current passes like this, it gets short circuited. Okay, so this you should remember. Next, is the last variety of problem which can come. So in the circuit shown below, determine IL, IZ, power dissipated in the resistance RS, the power dissipated in RL, power dissipated in Zener diode. So here we have used a Zener diode. So you know the Zener diode characteristics. So the voltage, the whatever the voltage we tell Zener diode voltage is 16 volt. Here VZ is equal to 16 volt. That indicates its breakdown voltage. Please remember, it indicates its breakdown voltage. This is not the voltage which is built because of uh, the input. It is the breakdown voltage which is already pre-designed. So this voltage will appear only when it enters to the breakdown region. When it enters to the breakdown region, when the input becomes greater than the 16 volt, then that too in reverse bias condition, it gets reverse biased and enters the breakdown region. So this 16 volt indicates once it has got reverse biased and it has entered to the breakdown region and it is maintaining 16 volt across its terminal. If you measure voltage across these two terminals, it will be 16 volt. Okay. So now in this case, IL, IZ, all these things are asked. So IS means the current through this. So current through this, you know that IS is equal to Vi minus Vz. Vi is this one, Vz is this one. The same voltage appears here. So current is asked means current through Rs is 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 equal to Vi minus Vz divided by Rs, because voltage is the potential difference between the two terminals. Whatever the voltage we have here and whatever the voltage we have here, these two are the voltages which the difference between these two voltages will be appearing across this resistance and current through this will be Is. So substitute it and you will get the answer. After that, the load current. Load current, you know that the current through the load resistance. And you can see the Zener diode and load resistance, they are connected parallel to each other. So whatever the voltage you have across the Zener diode, the same voltage will be across this resistance. That is voltage drop across the resistance. When you know voltage across this resistance, when you know resistance, you can easily find out current. So IL is equal to Vz by RL. Then after that, what they have asked, the power dissipated in the resistance Rs. So power dissipated in resistance Rs means you should know what is Is. So Is is equal to Iz plus IL, and Zener current also we have to find. So Iz, by rearranging you can find out Iz. Power dissipated means power. You can use I square or R V into I. It is left to you. So power dissipated across in the resistance Rs across Rs means I square R. I square S is the current which Is is the current through the resistance Rs, and this is the resistance. Substitute it, you'll get power dissipated. Power dissipated in resistance RL. So IL square, here IS square RS, here it is IL square RS, RL. Substitute it, you'll get power dissipated in Zener diode. So power dissipated in Zener diode, P is equal to V into I, Vz into Iz. Okay, because we don't know what is the resistance of the Zener diode. That's why we'll use Vz into Iz. So we will not use the Rz because we don't know what is the Zener resistance. That's why Vz is equal to Vz into Iz. Substitute Vz, 16 volt is given. Iz, you know that the current. So we'll get Vz. So this is the power dissipated in the Zener diode. Okay. So this is about the peculiar problems that you will be getting in module 1. Apart from whatever I have given in the textbook, you can just concentrate on this problems. Okay. So for today